So you can we don't expect that you have to learn all the code, but it should be that you should understand each line, right? If you are doing a freezing, you are freezing the parameters, or if you are defining an encoder, or if you are defining a decoder, you should know what each of the line means. That's what we have been covering from week 5 to week 7 so far, and we'll be doing the same in week 8 as well. That though sir has provided uh, a considerable good amount of code for each week. He has taken a task and tried to um, code it out. So our goal is that we should understand what each line of the code means, and you should be able to comprehend it. Or maybe you should be able to compute the number of parameters. See, number of parameters you can do by p numeral also, but if you have to do it on your hand, you should be able to do so. So those kind of stuff only you will be asked. Entire coding will be only in the NPP2. Uh,
So like if you want to like give us the advice like for the coding like to go through every line, what should we do like to
yeah, you
simply look
can just
for?
watch the all the TA session twos, like all those that happens on either Tuesday or Wednesday. So like from past 2 weeks I've been taking from Wednesday, otherwise it was Tuesdays only. So you just have to go through it, and I have covered each and every line of the code so that you understand what each line of the code means. Okay, some things might not. Sir has explained the major points in the in his lectures, but all the minor details, every line you should know. So that is more than enough, and I think so. Um, that does not will not take more than 45 minutes or so, because from week 6 or 7 onwards, the coding part is simple because you have already understood many things already, right? So those things will be easier for you. So it will take only 45 minutes to 1 hour. You can just go through it, and that will be enough.
Thank you, sir.
Yeah. Okay. Yeah. Many other doubts? So should I start with week 8 sentiment analysis then?
So one thing like how do you record this video in this Gmeet because I can't do like these things.
No, I am doing the recording, right? And it is being live on the YouTube also. So you can get the YouTube recording also, as well as the Gmeet recording also. So it
No,
is
sir. In
being done.
general, I'm asking. Like in general, I'm asking. Like if I want to teach in the Gmeet and I can't do the recordings and all.
So in your general account, it will not be there. If you are doing it with your IITM account, if you create a meet and you are the co-host or co-host for the host or co-host for that meeting, then you
Okay.
will have the option known as host controls. So from there
Okay.
you
Understood.
can
Understood. Okay. Okay.
be
Okay.
recording. And once you close the recording, you will get the recording in like maybe 3 to 4 hours max, and the link will be created and sent it to you on your email itself.
Okay, sir.
Okay. Uh, so can anyone tell me what you guys have studied in week 8? I think so. Pulkit has taken the theory class. What have you guys studied? Anyone can do a quick recap? What week 8 was all about?
Studied GRU and then LSTM,
Mhm.
RNN, the
Yeah.
extension of RNN
Yes.
to resolve this problem of vanishing and vanishing gradient and exploding gradient.
Yeah.
How we
So
this memory part, how do we keep this long-term memory short-term? How
yeah.
do we adjust it? How we add and then remove based on the current input,
Okay.
something from the past.
So if you remember, we were covering when we studied RNNs, we saw how the flow of the information takes place. And the problem was that we were doing everything okay, so there were two major problems. One was that we are doing everything sequentially, one at a time. right? One word is output, then that output is again taken as the input, then it goes on like that sequentially. So that means your computation is very slow, and that problem was resolved by this attention mechanism, that is multi-head attention mechanism in the transformers architecture. Okay, so that you will cover in maybe week 9 or week 10. The other problem of RNN was memory problem, right? So when if you have a very long sentence, then the problem was that while doing the back propagation, there was this vanishing or exploding gradients problem, right? So your numbers can completely die out or it might explode up, right? So these were the possibilities. Okay, to resolve this, we saw that there are something known as memory based RNN models, which you studied as LSTMs and GRU, right? So you studied the what is the simplified GRU, how it happens, and that is the full form is gated recurrent unit, and LSTM is long short term memory based RNN models. Okay, so LSTM was initially designed. So I'll just share my screen, and so I guess all of you like you have been studying. Is now we are in week 8, so you all have this my notes link, right? So I'll be referring to that. Okay, so more or the most of these things have been already covered by Pulkit in the Monday session. You can look there. So LSTM was introduced as a type of RNN which helped to solve the vanishing gradient problem. Okay, so it was particularly effective in learning the long-term dependencies in the sequential data. And what are the key differences with respect to RNN? First was the dual states, so it can go bidirectionally. Then we had this gated mechanism. This was for the GRU, gradient stability. It provides gradient stability. Okay. Next thing is GRU. GRU was basically a simpler alternative to LSTM. So they saw that LSTM was like it was good, but we needed something simpler, similar to RNN, but having um, the powers of what LSTM does. It remembers things, right? So there were two gates in GRU, update and the reset gate. Whereas in the LSTM, I think so there were four gates. Okay. So then this bidirectional RNNs were introduced, and finally we had this encoder decoder architecture. Okay, so today, and yeah, another important thing somebody mentioned also, this is specifically important when you do the text analysis kind of tasks like NLP tasks, natural language processing tasks, where you study this blue score, right? It is an evaluation metric used specifically in the NLP domain. It is a bilingual evaluation understudy. This is the full form. Okay, so this was the formula for this, how it does, and this was one example. What sir has explained. What will be the blue score based on what your BP is? BP is brevity penalty. We will see what will be the formula for this. So yeah, so sequence, another thing to note is sequence to sequence model is basically what this RNN is doing, right? It is a sequence to sequence model, right? The challenge was that which sequence to pick if they have the conditional probability. So one was the greedy search, so choose the best. So that would be basically and the problem with greedy search was that every time you will get the same result. If you see right now what like ChatGPT 5 or 5.1, if you use that, every time you use the same prompt, you will get different results. So you have creativity, right? There is another parameter called temperature, which does this help in increasing the randomness or decreasing the randomness. But this is essentially what we don't want same things, right? We want creativity, right? So greedy search was that particular thing. Exhaustive search is you search for everything, right? Like you find all the sequences, best possible sequences, which is computationally very heavy. And final thing was beam search. Beam, if you have a beam size k, that is a parameter, you just check what is the top three options that are possible. Okay, and then take it forward. Then this will have another three options. This will have another three options. So this is basically k times lambda. Okay, so lambda is how many tokens we have, and K is the beam size. So that will be the computational power. And finally, now we will move to this what is sentiment analysis code. Let's move there. I hope this quick recap was good enough for you guys, and now you have understanding what has been covered in week 8. So sentiment analysis stands basically what sentiment analysis means, that let's say the example here is from, I think so, IMDb dataset. IMDb dataset is a standard dataset again, and you have several kinds of reviews, right? This applies for restaurants, like Google reviews also. If you go to a hotel, then there also you check on, right? You check on your maps that what are the reviews, or you take a product from Amazon, you check what are the reviews for the same. How many positive people are there? How many negative people are there? So you search for those things, right? So similarly, this based on a particular sentence. Let's say I went to a place. The sentence is I went to a place. The place was good, hygienic environment, good food, good culture, something like that, right? Um, so that is a positive statement, right? So that is what is known as sentiment analysis. We are trying to understand what is the sentiment of that particular sentence. Okay, not us, but we are trying to train a model such that we give any new review, it should be able to classify whether it is a negative or positive. So you can have multiple classes. For now, I think so. We'll use only two classes, negative and positive. So let's start. I'll just connect this. Yeah. Uh, okay. So this is connected. So first thing is we check the what is the libraries that are required and what is the setup for this. So these things are usual that we have seen so far. NumPy for computation, Pandas for creating the data frame, data set, Matplotlib and Seaborn for visualizations, Torch and Torch.nn for bringing in the neural networks module. So we can define the encoder decoder architecture. This torch.utils.data, data loader and tensor dataset. First thing is we have to convert from a pandas data frame to a tensor dataset, and then we load that entire tensor dataset into a data loader, and we will be picking samples from this data loader. Okay. Then we have collections counter. We'll see what this does, and string import punctuation. Punctuation, we are using this. This is something new. And the reason behind this is that we have to, I just write it down also. We have to remove the punctuation. Okay. Remove the punctuations that might be dot, means full stop, comma, colon, semicolon, all those kind of punctuations from the. So actually, like for now, we don't need to train these things because so sentiment, we have the sentence, right? I went to a place, comma, the place was good, something like that. So we don't need this comma and dot things. So for that, we are using this punctuation. This is an library which is already module is present, which will identify all those punctuations from my sentence, and it will directly remove it. Okay. GDown is for the Google Drive, and we will be saving the dataset after downloading there. Then we have OS, operating system, warnings, and RE is for stands for regex. Okay. So these are the PyTorch version, NumPy version, Pandas, CUDA is available or not. We have already connected with the T4 here, so it should be available to us. And what is the CUDA version and GPU device, it will print. And we are setting the random seed as well as 42. Let's start running this. Okay, so this is done. Okay, moving ahead. Next is the data acquisition and exploration part. So we'll do some initial thing. So the data set is already available at this drive link, and we have the, if you see, let's say, if we can open this also and check it. It is not opening right now. Oh, it got downloaded. It directly got downloaded. No worries. That means that this IMDb dataset.csv is available, and it is showing me on my system also that it has been downloaded. We are downloading this IMDb dataset from this source. This is our target file. It will be saved here, and it tells you what is the size of this and in terms of MB. Okay, so I'll just run this. So it is downloading IMDb dataset.csv. This is the formula that converts, because the file size is generally given in terms of kilobytes. So we are converting it into what is the terms of MB, okay, megabytes. So this file is 63.14 MB. I think so. This should be available now. Yeah, see, IMDb dataset.csv is available too. Okay, great. We have this. Next, we read the CSV. First thing is we check what is the head, means what is the structure of this data set. So structure, I will tell you, it is more like you have these ID column IDs. These are not, this is just indexes, you can say. What is the review and what is the sentiment for this? Now you see this BR, this if you know a little bit of HTML, you would know that BR stands for I think so change in
Break.
line. Break, yeah. So breaking the line, breaking the distance space between two paragraphs. So I think so. This whenever this review data set was being created, that time it might be possible that this thing was uh, like taken from some web page kind of a thing while extracting it out. So therefore, this is the sentiment is given as positive. Okay. Okay. Next is we are calculating what are the dimensions of this data set. So shape would have given you um, x cross y, that is x is the number of rows and y is the number of columns. So we are taking 0 and 1, and it shows explicitly what is the rows and what is the columns. By df dot is null sum, it calculates what are the missing values, total number of missing values per column. Okay, so you can see that there are only two columns for us, review and sentiment. So this is just a part of index. Satya, I think so. All these are available. I'll just at the end of the session, I'll give you the link for the same. Okay. It has been copied, like kept it in a, I think so, in a Excel sheet. Okay, I'll just send you that. Okay. Next is we check what is the sentiment count. There are two types of sentiments, positive and negative. So we are taking the, for each of the class, what is the total number of counts that is available. Then we check whether the class distribution is fine or not, whether the means class is balanced. We have equal number of, at least approximately equal number of positive and negative reviews. Okay. Next is we check what is the review length. Okay, we are trying to get what is the statistics for this review length, and it will tell us what is the like maximum number of uh, words possible in our data set for this review, or whether it is small or big, whatever it is, it will tell us that. Okay, let's rerun this. So this is the data set structure. We have 50,000 rows and two columns. We don't have any missing values. Our review is 0 and sentiment is also 0. That means we don't have any missing values. The class distribution is very good. We have positive and negative. Okay. We have a very good class balance ratio as well. So it is 1:1. And this is the review length statistics. So total number of reviews is 50,000. Mean is 1309. The length of the, this is mean length of the reviews is 1309. Minimum is 32 and maximum is 13,704. This is a very pretty huge statement. So that's why we will be using. So you can see from the examples itself, there are some sentences which are very long, right? I don't know whether this is character or not, words, but even though it is very long. So to understand that, we need better architecture from RNN just to make sure to train our model efficiently. Okay. Okay. So this is ready. Now, here we are plotting our sentiment class distribution that we have found out here. Sentiment and count. This is just we are defining what is the height and width, just defining how this will look like. And finally, the distribution of the review length. So there are two things here. So let's see how it looks like. So sentiment class distribution you had seen, it was 25,000, 25,000, completely balanced data set. The distribution of the review length is, I think so, left skewed. This is left side, so left skewed. So this means that most of these are below 2000, right? So from the mean also we can say mean is 1309 and median is 970. Okay. So, and here we are getting a peak. So around 14,000 samples are there which have a frequency of, just a minute, please. Yeah, sorry for the disturbance, guys. So we can see that 14,000 samples are there, which have frequency of approximately 1,000. So this is our distribution of the review length. Now, next we do a sample review analysis. We take one positive and one negative sample, and we have to see what kind of character is there. Okay. Also, these are characters. So we can see these are the characters. Okay. Yeah. So one of the reviews has mentioned that watching just one OZ episode will you will be hooked. So from here we can see that this looks like a positive review. Basically, there is a family where a little boy is his parents are fighting. This that the pace is slower than a soap opera. At this point only itself, as a human being, I can say that it looks like a negative review. So these are just sample examples, and we will now start working on them one by one. Okay. Okay. Next we have this data processing. So there are three steps that we will that are being followed. First is the case normalization. As you can see, um, one in first sentence itself, the sample itself, O is capital. Then somewhere some things are like after full stop, this T is capital. So first we do case normalization. This is a function that takes every mm, uh, character you can say, and it converts it into a lower version of it. Okay, and we do this case normalization. We are taking one example and we are converting it the same example that we saw above. So you can see this O has been changed, then T has been changed to small t, and now next thing is removing these punctuations. If you remember, when we were importing the libraries, that time we saw that we imported something known as punctuation. So using that same library, we'll see if so the code here says that take all the characters. If that take those only those characters which are not in the punctuation. So you see, if you go over here, you can see these things, right? Uh, so these are known as punctuations. I think so. There are 25 of them, if I remember correctly. So these things will now be removed. We are taking the same example. These, yeah, see, these are the punctuations that is being removed. So it is doing this, applying this punctuation removal. And you see now that full stop will have been gone. Full stop is gone,
What
and
is
this
the reason to remove this? Why it cannot learn?
it can
What's
learn, but we don't want to waste our memory on those things right now because it will provide noise. Yeah, as Garang stated. Also, we are using we will be training. Um,
Eventually it will get learned, right? Not
Eventually, yes. It see it's a choice.
initially, yeah, maybe noise. But I see because that's how because say for example an exclamatory mark, many punctuations have a certain meaning in our language, right?
Yes, they have meanings, but the problem is our architecture is small now. If you are going to train an 175 billion parameter like GPT-3 on this, then you can send in everything. It won't have any problem to learn those things. But you have
Mm.
to see what we are going to use. We are going to use LSTM architecture, encoder decoder
Okay,
architecture.
okay,
The architecture is small, so we cannot afford to have much.
okay.
Yeah.
But
So and
in general, the LLM, whatever we are using, those things will not. We don't need to do this kind of a processing,
see, first thing is that
or
see
it is
if
not
you
processed like this for those architecture.
see, another thing is that even see, your computer when it is getting trained, it does not understand whether it is an exclamation mark or not. Okay, it has no knowledge of that. It does not have that sense actually. So it will also be tokenized and it will be given certain token ID. Okay, so only thing that it will it will think this house is great and it puts us exclamation. Okay, it feels like this is a joyous occasion, something like that or something like surprise occasion, something like that. It will just make some sense based on what it. So in generally, when you are training for big models, also we have this step where we remove this punctuation. We don't need them from the sentence itself. We try to make the LLM train that what should be the appropriate sentiment or summarization or whatever is there. But it knows because if you have seen the responses from GPT-3 itself from 2022, I think so when GPT-3 came, from that time itself, it knows what punctuation stand for. But during training, generally while doing heavy pre-processing, we remove those things. That has been a standard procedure. You can call that. Okay. Moving ahead, this is done. Next is now what we are doing after removing this. If you remember, this was our earlier statistics, right? So 1370, 13704 was your maximum and minimum was 32, something like that, right? So after doing this, your length would have definitely reduced. So that's what we are checking here now. So we are just checking what is the clean text. Yeah. So this is your clean text length have reduced. Your average text length reduction is 4%. Generally, this happens. There is a 5 to 10% of a reduction just by removing the punctuations. So these are just characters, so we have removed them. Now, earlier, your average was somewhere around 1200 to 1300. Now your average is somewhere between 930, so which is good. Okay. Now as we all know, that we won't be sending this um, text directly, right? LLMs don't understand what text is. Okay, it has to have some kind of a numbers to train on them, right? So now we need to tokenize these text or whatever reviews we have into some form of numbers. So we have seen in the lectures that we build a vocabulary. Either you can take a predefined vocabulary or you can do this what it is called or you can build a custom library vocabulary as well. So let's see what happens next. Yeah, so we are creating the corpus for vocabulary construction. So we are going to create this based on what we will search for the entire 50,000 reviews. We'll go through each one of these sentences one by one and we will check how many are the total number of unique words. So based on the total number of unique words, we'll create the vocabulary. Okay. Uh, we will also these also it also tells so it will calculate the word frequencies for each of this, and for the same thing we are using this counter that we have um, imported this module from, I think so, collections library, right? So, and it also calculates what is the most common words and what are the least common. So the might be the most frequent. Okay, this is possible. See, so that creating corpus for vocabulary construction. So your total words is somewhere. I think so. This is 11 million, right? And the unique words are only 181,000. So which is almost 100 times lesser than what earlier this total words in the corpus was. So the most common words are the and so these are these kind of words we expect to have in the sentence. So based on that, we have this. And then we have this least common words in vocabulary. So these are like effortful, fun occurrence. I think so. There are these things might be somewhere it can be mistake also. The reviewer who was giving the review might have some mistake as well. Okay. Next is creating word to index mapping. Now, um, each now we have these unique words in our vocabulary, right? So they all have to be mapped to a unique index, right? Unique index like from 0 to whatever is this is if this is n, then we will have n minus 1. The mapping will go till n minus 1. So okay, so interestingly, we are starting from 1 itself, so it's good. So it will go till 181,685, whatever is the words. So word index 0 has been reserved for padding. Now, why padding is important? If you remember, see, I'll just show you an example. Yeah. So there were some sentences with only 32 characters. There were some sentences with, so your average was somewhere between 1300 something like that. Other was very long also. Okay. So yeah, we have to make sure while we are training our models that if there are these empty spaces, so we will define one context window. If there are some empty spaces, those empty, let's say if this is your context window, okay, this total is your context window, then this much region and this much region, this region and your this region will get the pad token. Okay, we will see the importance for it later, but this is the idea. This is what we are going to do. Okay, so let's run this. I think so. I've run everything about it. Yeah. So vocabulary sample, and we have this word index. So this is how it is going on. So the is 1 and 2 3, something like that. We have created it, and index 0 has been reserved for the padding. Okay, now now what we are going to do, we have the vocabulary ready. Now we have to map each of the reviews to this number sequences, right? So let's say my thing was the house is great. Okay. So let's say the I got vocabulary 1, so I'll get 1. So it will be a vector, right? Each review now becomes a vector of these numbers, right? So the is, let's say, 1, 5, 0, not 0, comma 3, comma 2. Let's say these are the numbers. And if you define your context window more than 4, I think so the house is great is 4 words. So you will have 1532000 till your context window ends. Okay, so that is what is known as padding. So this is how your each vector will look like now. Okay, so this is what we are doing in this code snippet. We take this text review, we have split the reviews. Then we are encoding these reviews as integer sequences. You can call them vectors as well. Finally, these are some example. One example has been taken. So this is what I was telling you also from the example. The house is great. So we'll see. So original text was this. One of the other reviews had mentioned that after something something. So 28, 4, 1, 77, 1941, and it goes on like this. Okay.
And
In
this number is given for each of the words lexicographically, or how it gives?
it the from
For the
the
unique, words, I'm asking.
yeah, it is not lexicographically. It is how it was present in the list. now when I started calculating the unique words, right? So maybe my unique words when it started, okay, let's think like
It
this.
is
Your
based on
total,
the frequency, no? Uh,
uh,
what we have defined in the earlier cell is
yes,
like that.
yes, I was explaining that only. Yeah, yeah. So see what we did, the process, if you remember, we found out what is the total number of words. That was 11 million. Maybe then there was a sorting, and this has been in a decreasing order of in frequencies. Okay. So then when you take a set of it, then you get these unique words. Now your unique words also, your set will have everything how it would have been in the list itself, the previous list. So on the base of that itself, this vocabulary is being created. The, if you remember
Based
this,
on the
the,
frequency, the number will be given. So
yeah,
higher
yeah.
frequency will be
For
one,
this example, you can take
second
any
highest
example.
will be two, like
You
this.
can do anything else also. It is not necessary to do this as only. You can take minimum also. You can do it arbitrarily also. Just that every unique word will get a unique number. That's all.
Okay, everything works. Or
Everything
is
works.
there any guidelines for
No,
doing
no.
these
There
things?
are some certain guidelines which have not been covered in the course right now. If you take subject LLM, a large language model, then you will study. There are certain guidelines to
Okay.
create a vocabulary. Okay. Creating this many words is also not appropriate actually. I'll just let you know. This many words and generally vocabulary size are 30 to 50K. This is the general vocabulary. But right now, what we are doing, we are just taking white space as your separator, right? This is not this does not happen in actual practice. There is a tokenization techniques, byte pair encoding. There are 3, 4 techniques that are covered in large language model course. So there you will understand how you can get a 30 to 50K kind of a vocabulary size. Because when you do it in the transformer architecture, this actually multiplies itself. That is the matrix size. So we want less computation also. So all those things are for future thing. We don't have to refer to that right now. Currently, you can think that each word separated by a space will be my one token. Okay, you can think like that. This is what we are doing right now. So minimum length is 4 tokens, and your maximum length is 2469 tokens. Your average length
Sir,
is 200. Yeah.
sir, in vocabulary, all the words are unique. There is no repeating.
Yes. No repeating.
Okay, 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 sir.
So how is it storing the vocabulary? I mean, where is it? What is the
Currently,
data
you can
structure?
think it is a dictionary, na? It is a dictionary. For now, you
Okay.
can think of this as a dictionary. You see, we are just we are defining it in a dictionary. See, word. It is like a key value pair.
Yes, yes.
Yeah. There are better ways. Please don't delve on that. Right now, think of this as a dictionary. Okay. So your
These
average
things
length.
write code for doing all this pre-processing currently. There is no such libraries for.
There are libraries. It has not been covered here.
Okay, now we are going through how to do it from the bottom, from the
Yes.
scratch we are building.
And these things are not used in actual practice. Okay. We don't take entire word as a token. This is not what is used recently in the industry. There are other methods, but just that we are trying to build everything from scratch. That's what we are learning here. This is the basic thing that you can, right? You can make a space. Either you could, what you could have done, you could have taken every character as your token. So that will be 26 characters because everything has been normalized. There will be no new word. But then a number of tokens will be huge, right? But right now it is like somewhat between a trade-off. Okay. Yeah. Now we are encoding the sentiment labels. So for positive, we are saying it is 1. And for your negative, we are putting it as 0. Okay. So this remains same. Earlier also it was 25,000. Now also it is 25,000 itself. These are two, I think the distribution of review lengths now in terms of tokens. Earlier it was in terms of characters. Now it is number of tokens. Sample of short reviews. So we have taken one sample, which is a short. 1. So see, these are the number of tokens. So tokens is, I think so, mean is somewhere between 230. Yeah, so I was expecting 250. Yeah, this is what. So more suspenseful, more subtle, much more disturbing. So 8 tokens. Okay. Read the book, forget the movie. 6 tokens. Primary plot, primary direction, poor interpretation. 4 tokens. Now, primary is one word. Plot primary, plot exclamation mark primary is another word. Direction exclamation mark poor. So after normalization, what it will become? Direction poor, plot primary. These things exclamation mark will be removed. So interpretation, and these are your encoding style. Okay. So these are just examples. Now we move to dataset preparation for our neural.
Basically, this one, like more frequent words will be close to the origin, and then least frequent words will be somewhere it is mapped long.
Yeah, very far off in the
Far off
vocabulary.
from the
Very
origin.
uh
The more greater distance, it will be somewhere.
very huge distance. Yeah. You see 180, 100,
Which
181,000 tokens are there, na? You see, plot primary has been allotted 139,000,
who will use
and
that?
your direction poor is allotted 139,000. It is very huge. Means very far off in the vocabulary.
We don't use these words. So it is given. Okay, this is a good technique.
Yeah,
Giving the frequent word as one, and then from there. That's the good technique.
yeah. Okay. Okay, moving ahead. Data set preparation. These things are more or less same. So what we are doing, we are padding these features. So we have a sequence length and we have the length of the reviews. So we will have these tokens, right? Sequence length has been defined as 200. Okay. So now every sequence will be standardized to that. So earlier, let's say you had 4 tokens, no? So that also will become, it will be added 196 pad tokens, and that is zeros. 4075, 139, 486, 139, 487, 2903, and after that, all zeros will be there. So we are padding those features. So zeros plus review. Okay. So example of a standardized sequence, original length and padded sequence. Again, long review. If it was a short review, it will be padded. If it is a long review, it will be truncated. Truncated means removed. So excess parts will be removed. Okay. So we see example for this now. So we
What
see
is this convention? Why we are
convention.
taking this such a convention?
Because
Padding
when you
is reasonable, but long review truncate means what if the actual negative or positive tone is after the truncation? It is
then
coming
you
out.
lose that information
Yeah, that
info.
we. So why we for adopt this convention of
So basically, the
short,
point is
short review
that
padding is okay. Long review truncate this convention. Why we are.
yeah. So what I was explaining that. See, what happens is whenever you train an LLM, there is something known as a context window, right? If anybody would have studied LLM architecture, there is something known as sequence length. Okay, so there is some up to some certain part. Sequence length is for the input, and context window is how much in one go your LLM can understand. Generally, for shorter, small models, if you have a small parameter model, then your context length will be that size, the window. That window length will be small. And currently, I think so. It has it can accept a maximum up to 512 only when this LSTM and these things were introduced. This transformer architecture, when it came with this self attention, multi head attention, it was able to understand up to 1 million tokens, which is currently the GPT-5's limit. Okay. So we need to remove those things. And you pointed out that let's say if your negative thing was after 200, then that means you are losing that information. That's why these are the problems that you face while training. Okay. There's some things which some things have solution, but many things don't have solution. That's why people are still working on it.
So this one is primitive, so these kind of things comes.
Yeah,
Currently,
therefore your sequence length is small. Now, when your GPT initial GPT was trained, it had, I think so, some 1 billion parameters, something like that. That was also GPT-2, large one. It had 1 billion parameters that it can accept. Means 1 billion parameters that it could train. Then that is it a matter of hardware limitations? To some extent, yes. Okay. Now,
sometimes I try to write this in Gemini. It accepts only 2,000 characters.
yeah, so it is possible. So I don't think so. Now Gemini 3 has that problem. Earlier models were had this problem. Now their context window is more than 1 million, which is very huge.
Oh, while we are prompting it.
Yeah, yeah, prompting also. Now their context window has increased at a huge level. You can try I think the Gemini 3 is available for preview in your Google AI Studio. You guys know about this, you can play with that. Okay. Okay. So this is an example. It is showing that 200 tokens is the sequence length. And if you remember here what we are doing, zeros plus review. So earlier at the initial level, all the zeros are there, and at the end, all the 4 tokens will be there. So if this was your 2469 tokens were there, then it will be truncated at 200 ones. Okay. Now we are doing this standard thing of converting the data set into a training, validation, and testing set. So we are doing this. So yeah. So I'll just run this. So you can see training set is 40,000 samples. Your validation is 5,000 and your test set has 5,000. You can see across the split also truncated the rear words. Yeah, yeah, yeah. The yes, rear word. Yes, rear words. The which are present at the back portion, whatever you call it. From the right side, you can say that also. Class distribution across splits. So full data set, 50% is positive. That means 50 is negative, which is good. Training set again 50% is positive. Validation is 50.7% positive, which is almost approximately the class is still balanced. And your test set also 49.4% positive, which is again comparable. It's good. Once we have this, we create the PyTorch. We first of all take this whatever from the NumPy. We have these columns, right? So we can take it as a NumPy vector. Huh. Um, yeah. Then we convert them into a tensor data set, train data, val data, and test data. And from this, we convert them, we store them in somewhat something known as a data loader. And we have a batch size of 50. Okay. So these are your data loader configuration and your sample batch inspection. We are just checking what is the batch shape. Okay. Running this. Batch size is 50, training batches. So whatever was the total number of samples divided by the batch size. So that is 800, 100, and 100. You have sample input, tensor, and this is a label corresponding to this particular sample. Okay. Next, we define this model architecture now. This is the important part. Here we are defining the RNN, sentiment RNN architecture. The sentiment is just we are given a name to it. Basically, it is an RNN architecture. So the total number of layers, how many hidden layers will be present? What will be the hidden dimension of them? What is the embedding size, which is essentially your vocab size into the embedding dimension? Okay, these are basic mathematics that you should know. These kind of questions somebody asked me in the starting of the session, right? What kind of questions we can expect? These kind of things you should know. Okay. Then you finally define this RNN architecture with these embedding dimension, hidden dimension, number of layers. Dropout probability, dropout, I hope you remember from the initial weeks, your dropout is specifically in the training time. It's not used in the testing and inference time because what we want is mm, uh, to not have any kind of a bias with respect to sentences that are incoming while training. Okay. Finally, we have this fully connected linear layer. After all these hidden layers, we have this fully connected linear layer, which is the dimension for that is hidden dimension and the output size. So from here, after this embedding, RNN architecture, you got hidden dimension, right? From hidden dimension, you have your input linear layer, and your output size, which is your expected output, will be your the outer dimension, right? Finally, on the top of it, you have a sigmoid. This is just to bring non-linearity. Finally, we have this forward pass. What we are doing, we are defining batch size, defining the embeddings, RNN output, and hidden. We define what are the dimensions for them. Dropout at your this layer itself, your hidden layer itself, we should have a dropout. Finally, we have a fully connected layer, sigmoid, and sigmoid output view, how the output will look like. Okay. Initialization, RNN model architecture. Let's see what it looks like now. Okay. Let's see. So your input dimension, first of all, was 181,686. So your padding was 0 and 1815685, I think. So were the unique words, right? So that is your input embeddings into 400. Then your RNN architecture is 400 cross 256. Two layers are there, and dropout is of probability 0.5. Then you have a fully connected linear layer after the two layers of this RNN recurrent neural network. Your input features is 256, and your output feature is 1. You will only define whether it is positive or it is negative. Bias is equal to 2. Sigmoid will give you an value, an activation function, just it will give you the value. So the total number of parameters is 72 million, and approximately this model size, you can see each element has a particular size, and then there are total number of parameters. Then if you multiply them, you will get the model size in terms of megabytes. So first of all, you will get in kilobytes. Then you can convert using the standard formula, divided by 1024 square. You will get the approximate model size. Okay, so this was your RNN model. We are also defining an LSTM model. Okay, so everything remains same, just that it will have a longer, it will have a good memory system. Now you see, this is 72 million parameters were in RNN. LSTM has 73 million. So LSTM has 400 to 256. The number of layers is 2. Your FC is this, and embedding was this. Everything, most of the things remain same. So there are approximately 1 million parameters in LSTM, more than what RNN had. Okay. Now, yeah, Aditya, please tell.
Sir, if there were multi labels, then instead of sigmoid, we can use softmax.
Yeah, and your what will be your output features? If you have 10 classes, your output features will be 10.
Okay, okay, sir.
Yeah, Aditya.
Sir, this inside the tensor dataset, sir, we are not defining the class. We are just using that function tensor dataset for
Yeah, so
RNN.
it is itself a module now, so we can directly use it.
Okay, sir. Okay.
We don't have to define it. If you remember, in week 1 or 2, we had learned how to define this dataset, but which is already available, we can use it. It's okay.
Okay, sir.
Okay. Training configuration. So these are the standard things. Batch size was 50, learning rate was 10 raised to power minus 3, 5 epochs, clip 5, print at every 100, we will print what are the statistics. We are using a binary cross entropy loss. So since this is a classification system and there are only two things, the binary output, whether it will be a positive or it will be a negative, only two options are there. So we are using a BC loss. We are defining two different optimizers for RNN and LSTM. Okay, but the learning rate is exactly same. We are scheduling this on this principle, reduce LR learning rate on plateau. Okay, mode is min, factor. So these things you have studied in week 6 or 7. Not repeating this. Patience is 3, minimum delta is 0. So minimum delta means minimum change in the learning rate. So this is the minimum thing, and we define the this. So this is our training configuration. So let's run this. I think so. This should work faster. Yeah. So early stopping criteria we have given as 3, patience is 3. So we have to check that for 3. So what this means is, if till 3 epochs you don't get you get this fixed delta, then after that you can stop earlier also. This is what it means. Model training. So you are calculating these metrics from YPRED. You check whether your YPRED and Y true. You have to check the threshold. And based on that, these are the general metrics you would have seen in machine learning practice also. When you do a classification problem, precision, recall, and F1. These are the standard metrics. You can move on and go to ROC, AUC score, those kind of stuff. So these are your metrics. We are calculating them. This is the function for that.
Sorry, what is that threshold in calculation metrics?
Yeah. So basically, if threshold is 0.5 most of the time, so if it's more than that, so if you remember, you are getting sigmoid now at the end. So it will give you a number, it will give you a
Oh,
probability. For
okay.
that, we are putting this threshold.
That is uh, that is not inbuilt. We have to explicitly state threshold equal to 0.5.
Yeah, means there is no default value. So threshold is what we are defining, right? So you can take anything else also. Generally, default setting is we take it as 0.5.
Yeah, that's what I'm asking. Okay, if we don't give threshold also, it will be 0.5 only, no?
No, 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 no. Threshold is not originally defined in this. We are defining this class. No, this is our parameter. This is not a sklearn or torch parameter. So we
Oh,
have to define it.
okay. This is
Not
not for sigmoid. We are
yeah, yeah.
for our okay. Okay.
Then we calculated this. Finally, we have this train epoch. So output H loss has been defined. You backpropagate the loss. You clip the extra gradients if there are needed, and finally you update your parameters. Calculate the loss and move to the next epoch. It goes on like this. During the validation, we don't do this model training. We calculate the validation loss and that's it. Same goes in the test loss also. We don't update the parameters in validation and testing. Okay, run this train model, save model to the best. This is same thing. We're defining LSTM. Okay, so okay, now I don't know how much time it will take, but I'll run this. Okay, I'll run this. Let's see how much time it takes. So it will first do the RNN training, then it will do the LSTM training. So you can see what kind of a loss we are getting. It is at every epoch it is decreasing. Here it increased. So it will go on like that. We'll move to the next part. We save the best model, RNN best and LSTM best in our models. This will be saved here itself. You can save it also and you can use it somewhere else as well. So this is the model comparison, test loss, accuracy, precision, recall, F1 score, and training time. So this is what we are doing, and we are calculating the difference as well. So this was the earlier parametrics. You can see LSTM model has done a lot better. So you see LSTM accuracy improved over RNN was 14%, whereas its training was almost 50% slower than what RNN does. So if you would have seen, I think so RNN is almost trained now. Yeah, so the first epoch is completed. I think so there are 5 epochs. Okay, so it will go on like that. Second epoch is kind of come. So 1 minute it took to calculate 2 epochs. So for 5 epochs it will take 2.5 minutes, and LSTM will be much slower. It will take 5 minutes to calculate that. Okay, so this was the earlier results. Now this is we are just checking for the plots how it looks. So training loss RNN started from 0.66 if you remember, and it will go up till 0.35. Whereas LSTM started somewhere between 0.55 and it goes to almost zero. Validation loss somewhere here at epoch 2. This is it has overtrained, so it is getting this kind of a curve. Validation accuracy and validation precision. So you can see Epoch 2 was, I think, so best for LSTM. As over the time, that got better itself. I think so 0.2 was
So
the
why is
best.
that loss is increasing in the LSTM?
This part, right? So it means that at certain point, see, we had what? We had how many tokens were there? I forgot. There was 181,000 tokens, right? And there are certain number of parameters. At certain point, what happens is even if you like, you will have to see. That's what how this transformation has happened from perceptron till what we are seeing today, the large language models. So your data set size and your number of trainable parameters both should increase considerably. Like both should increase in proportionate. Otherwise, this happens that if you have less number of parameters and more data, then it will learn too much. So training loss got to zero, but our validation loss increased after Epoch 2. That means that Epoch 2 itself, it had overfitted. You don't have to go above that. Means it is not able to perform better than that. So this is what it is. I hope it is clear, Satya.
Kind of, sir.
Okay. Okay. These are model performance comparison on test set. How you can see LSTM has done well because it had learned well. So there were more number of parameters. It was able to do well. So we have here is just one simple function. What it does is you can input your own review. Okay, so you can just enter something of your own, enter your movie review or type exit. So you can put in your, this is a kind of a UI kind of thing. Okay, so there are certain examples. Analyzing review. Okay, the special effects are very amazing, but everything else about this movie was terrible. So it is negative. RNN says negative with confidence 94%, and LSTM says negative with 99%. So both models agree. Both models agree. Sometimes models might not agree also. So if you write a very tricky statement like this was better, but that was not good, something like that. So it will have a hard time in analyzing that. So I think so. This execution of the LSTM model is still going on. No worries, but you have seen what the entire notebook looks like. Yeah.
Diplomatic answers.
Yeah. So I guess that's it from my side. We have covered the VK concepts thoroughly. Pulkit has covered all the theoretical aspects. I've covered the entire notebook, at least all the important parts and whatever each line means. Few
Uh,
things that I've left, these
please,
things have been.
sorry, can you please tell about this embedding in the input layer?
Yeah, which part? Let's go there.
What is actually happening in embedding layer?
Okay. Where it went. Yeah, here, right? Yeah. So this is so okay. So when you are doing an input, right? What happens is that there are total number of tokens, that is unique words is 181,686. Okay, and we know that your hidden layer size is 400 cross 256. So what embedding does? So currently your embedding is very simple, right? Um, it just takes the input, take whatever the sentence is there, along with that padded sequence, everything, all those things. It takes in the input. Okay, so I'll just try to show it. This is your let's say your input sequence. Okay, so this is your input sequence, and this is the layer, first layer, that is the embedding layer. It takes this, whatever is the thing, and it converts that entire sequence such that, so basically the task of this embedding layer just to make sure that it should reshape it, squeeze it, or whatever it has to do to make sure that the hidden layers should be able to process it. So it should be acceptable for the input size of the hidden layer. So this is the action of the embedding thing. In future, what you will see, it will have more functionality than just reshaping it or squeezing it. Will have much more functionality. Like it will some at in I don't know, not very like big future, but um, it will add position encodings. So what it will do, it will take your hx, whatever the position, whatever your input sequence was. Let's say your it was x, then this embedding will also do something known as, it will plus the position of that x. Okay, so for right now it is not doing much, but it will have greater functionality when we study further architectures as well. For this week, you can think of it like just reshaping such that it is able to get into the LSTM RN model, means the main architecture part, which is this hidden layers, right? These are the hidden layers where this LSTM is sitting, or the GRU is GRU, or whatever we are using. We have used RN and LSTM, right? Yeah, so RN and LSTM. This is what.
Okay, somewhere you said context window and we set the sequence length.
Yeah,
So
that was earlier. That was earlier itself. Before coming to this place also, before coming as the input
there
also,
itself we are reshaping. No, why again we are doing?
no, we were reshaping such that uh, we were not reshaping. We were just making sure that our input is standardized. We are not doing anything else. To
So
move,
that itself we can feed into the next layer. No, the hidden layer. It
uh,
can't be done like that.
no, I can't explain you the. I also don't know how internally it works, but this is for sure that you cannot skip this part. You have to go through this
So this
because
embedding layer must be there.
must be there, and you can call this input layer also. And what happens is that, see, things are created when things have been created from the past till today. There is some standard architecture, right? So this standard architecture itself will get better over the time. So as far as the standard architecture is concerned, you have to have this embedding layer. But as you will see, yeah, Gorang, answering your question as well, that time your f of x, this thing at this position, it will add something known as positional encoding. In future, it will do something else also. These things you will study, I think, so in week 10 itself. This position encodings. So that's where you will learn that this had to be there from the previous architecture itself. We cannot change the architecture completely, but we can add something consistently across through it, right? So this is what the major concern is. Yeah. Yeah, I was telling you something. Okay, I've forgotten now. Okay. Just saying some before saying something. Somebody had asked for this notebook, right? I'll give you this link.
It's the Excel sheet for the.
Yeah, yeah, yeah. Thank you. Yeah, I've shared this. Yeah. That's it from my side.
Yes, sir. Thank you.
Sir, I have a doubt.
Yeah.
In RNN definition of PyTorch, what is this number of layers?
Number of, where you're saying this type, this thing, right?
Num underscore layers, yeah.
Yeah, yeah. So that is the number of hidden layers that will be available in this LSTM model or in the RNA.
So
So
hidden
you
layer
see,
means,
I'll explain. So let's say this was your input, your embedding layer.
okay.
Then you have these two hidden layers. This means drawing this. I'm trying to draw this architecture. Okay, there are two hidden layers. After that, within this also itself, you have a dropout. Okay. After that, you have a very long this FC layer, fully connected linear layer. This is your linear layer. Okay. And finally, before going to the output, here you have a sigmoid layer. So this is what an architecture looks like, somewhat.
Okay, all right. So it's individual RNN units, two RNN
Yeah,
units.
yeah, you can call that. Yes.
Okay, all right.
Puneet, actually, when we go through this lecture, right, or the YouTube videos,
Yeah.
the difference between the RNN and the LSTM or the GRU,
Hmm.
there the weights becomes 4 times. So compared to RNN, LSTM will
No,
be
no, no, not at all.
3 times in the GRU, because one level we are reducing. Like that, there was
No,
some.
no. See, I'll just tell you what RNN was doing. Let's say this was your input. Okay, I'll show a very small diagram. This was your input. You sent an input here. This was your H naught. This is your X1. Okay, I'm not writing it. Just remember it like that. You got some output. Okay, F1. Then this thing goes in here as H1, and this will come in here, right? Something like this. RNN does something like this.
RNN was very simple, right? Because
Yeah.
your H will
Only.
be equal to WX and then UH
Mm,
or whatever it is. This is the
mhm.
linear combination. But when you go to LSTM, we have 4 equations, right? For
Four
that
equations, but
memorizing.
see,
So that many, and all those equations are same only. It is finally WX plus UH. Only thing is you apply sigmoid and then multiply with the just to forget. You have a forget gate where you take the sigmoid and then take the previous and then try to,
you add something like this, right? You
and then
add something like this.
yeah.
Yeah.
So
So,
here there are so many 4 equations, 4 W's and then 4 U's, right?
mhm.
So, but here when we see the number of when we see, we were having only 1 million difference.
Yeah, that's what I'm trying to explain. See, uh, from RNN to LSTM, it is not like the number of parameters becomes like too huge. See, there are only two, three gates that gets added. Like there is one forget gate. There is one thing called some reset gate is there. Some more. I think the three or four gates are there. Okay. Now those gates does not, basically it was introduced just to make sure
Forget
that,
input output.
sorry Satya.
Forget gate, input gate, and output gate.
Yeah, there is some reset also. I think so that
And
came
that
in
is for
group.
the
Reset
GRU.
comes in GRU.
Yeah,
Reset
yeah.
comes in GRU.
So there are, let's say there are three gates. Okay. Now these gates, what it is basically, it is trying to do that it is helping you when you, while you are doing the back propagation, it helps you to pass the gradients across those gates also. Okay. So the relevant, uh, how should I call it? Relevant number, that is the required number, should reach that particular vector as well, right? Whatever was there, its importance. So that's what we are, while we are back propagating, this happens. So those gates does not have very huge number of parameters. I don't know from where you saw this reference, but it does not
Because
increase the
see,
Just a minute, just a minute. It does not increase the parameters like huge. It is just, there are some parameters that gets introduced at each level just for that those gates, and those are not very huge in number. Yeah, you were saying something. Please tell.
actually, you have that block diagram with you. There is a block diagram explaining the forget input and output gate, wherein you take a sigmoid for the forget gate, you take a sigmoid and a tan h in the input, and then tan h and again sigmoid in the output, where every sigmoid function which is taking the previous CT C T minus 1 and the X current, right? It is
Mm-hmm.
learning different weights, W's and then U's. If you have the block diagram, it will be very easy. Or even you have four functions, right?
Yeah, I've presented
Four
it on your
functions have
screen,
four different weights, right?
but it is not huge, no?
No, but see, your RNN has only one formula, one function. You have one set of W and one set of U to learn. But if you have four
I understood
formulas
your point.
and
I
four set of
understood your
W's
point.
and four set of U's for the which is taking the same CT minus one and
You
X.
you forgot one important thing. There is something important that you have to remember, that these are shared parameters. If you are doing the sharing, then how will the number of parameters increase?
Yeah, I was also under the impression, but when you go and see the function, they don't
Uh,
put this W as W in all. They put WI, W. If you see the formula, the W index will be varying for each and every formula. The same way, U index will also vary.
no, no, it does not vary. It
See,
see
you put
you
WR, W, U, and W something, right?
your W. This is WH.
If it is
This
a
is
common W,
WZ.
then I agree.
Uh,
Sir, I think he is correct. We came across like that only. Three times GRU will be three times parameters, and
LSTM is
LSTM
four
is
times.
four
This is what
times.
I'm confused because the
But
based on the
here in the lecture, I think sir has explained clearly. Embedding layer also has parameters, I think. So that is common in both RNN and LSTM in this implementation. So that's
oh,
why the difference is less.
okay.
Something like that he explained in the lecture.
I am with you because this shared when you take the sigmoid,
Hmm.
all the input, your forget and the output takes the sigmoid function takes the same x from the current layer for the current input and
Hmm.
the previous ct minus 1 it takes,
Hmm.
but the w's what they say is it's a different w, it learns different. I don't understand that itself. It should be shared. I agree with you
Hmm.
because if you go to the block diagram,
Then you are
the
correct. Then
same
if
x
you
and the same this one to all the sigmoids, why
if
it
we
should be.
take these three separately, then yes, it will increase. Yeah, yeah,
No,
that's
but
true.
if you go to the block diagram, I do not know. I'm still. This is one of the question I have to check how passing the same xt and then same ht minus one to a sigmoid will learn different w's
They have
just
written here
because it is an
also.
input layer and a memory layer and sorry, the forget layer, input layer, and output layer.
They have written here also. Original LSTM had 4x times the vanilla RNN.
I
Hmm.
really don't understand. I'm still confused on that. Given the same xt and same ht minus 1 giving to the sigmoid, just because the sigmoid is in the forget input and output layer, how the weights it will learn different weights. This I'm not able to understand.
Yes.
Sharing, yes, I agree. It should be sharing. It should be the same weights in all the layers for at least the sigmoid because it is taking the same xt, same ht minus 1 from the previous.
I think so. Instructor would be able
But
to answer
the
this
purpose of
question.
the
Then,
W's is different, right? So
then the learning
actually,
would be same for forget input and output, no? If it is same.
Yeah, if we keep everything same, then all the parameters will have same
I
values,
don't
right?
want to, but
yes,
mathematically, give
Hmm.
taking the same input, right? 1 into 2
yes, this input
plus
is
3
same, but
into
the
2.
purpose is different,
Everything.
na?
How it will happen mathematically? I'm not okay. Maybe this is happening as it is.
Look at the Hadamard operation. No, it is like the operation is between two separate things. So like you are correct. It will like for the first time it will like converge
After
towards the
many
same. But
iterations, we are
during like
applying.
back propagation or something like that, the update will be different. That is why the parameters will differ.
Karthikeyan,
Plus
does this answer your question?
initialization on top of that. We are initializing different, so that is different. And plus, even if we were, by your logic, like they should like converge towards the same value, but that is not happening because the Hadamard operation is between two separate things. So when let's say one epoch happens, after that, like let's say during back propagation or something like that, uh, when the values are being updated, the updates are different.
Yes, exactly. Their gradients are different.
Yeah, so like you do during normal neural network, you do del L by del W1, na? So uh, the way W1, like say here WF and WI will be affecting the loss function, that will be different because of the operation that there is, which is why the update values will be different, and consequently, hence, uh, the final parameters will converge to different values.
This we need to see at least one or two small problems, then see it, and then back like we did the previous, I think week 5 or somewhere, or week 4 or 3. We did back prop, maybe only one time. Like that, maybe we see, then we see it still, because the change is based on this, right? Okay, loss. Okay, I back prop. Based on the loss, I back prop. But the rate of change is taking the same ht minus 1 and xt from the previous layer. It is going to be the same. Still, mathematically, I'm not able to convince myself. Maybe we need to do a problem wherein we need to take only two layers, two set of forget input and output, and then back prop and see the values are different. The learning, the W's are becoming different for
Hmm.
each.
Okay,
And
you can pose this question to instructor session as well. I think so. They might be able to answer this.
I was just waiting for Levin to come, so that I just wanted to check with, maybe he has
Yeah,
some
yeah,
resource wherein he can help
yeah.
us.
So I guess you guys know about D2L.ai, right? It is a very good like, website. You can refer
What
to
is
that.
it? D
D2L.ai.
D12.
It's the book from Ian Goodfellow, the person who started this deep learning, all those stuff.
Satya posted it in chat as well.
Yeah, you can refer to that website. It is a very good book if you want to book and practice. All those things are available there, so it might help you out.
Thank you, thank you. I
Yeah.
do not have any other questions.
Sir, a
Okay.
small
Yeah.
request. Could we do a parameter calculation question for the RN, LSTM or RN, which was in the collab notebook?
Uh, you won't get at such huge level. Na? You should refer to those questions only which you have been given in graded assignments or practice assignments. Then you
I
will have
don't want exact calculation, but at least what multiplied by what, just for a single LSTM layer
okay.
with two hidden, two number of layers. Only for the LSTM one.
Hmm. Okay. Where is it? Just a minute.
Or if it's too complex, then we can do
No,
RNN as
no.
well. It's quite similar.
I will do for RNN. Okay.
Okay, all right.
Let me connect to my no writing pad. Mhm. Okay. We have this ready. Okay. Let's start doing this. Okay. I'll write it on the screen itself. I hope that's okay. Okay.
Okay, it's okay.
Okay. So first is where we have embedding layer, right? Embed layer. So first we have to
Embedding,
calculate.
we can leave it. It's easy to
No,
calculate.
no. So we'll do for this example, and later, okay, later you can see. This is what? This is your embedding dimension, right?
Yeah.
This is your embedding dimension. What is this? No, sorry. This is your vocabulary says this is your embedding dimension. This is your embed dimension, and this is your very easy. This is your vocabulary size. Vocab. So vocab size into embedding dimension. So this is 181,686 into 4. These are the total number of parameters that are available in the embedding. Okay.
Plus 400 as well, na? For bias.
Let's forget the bias. It will not make much difference, but yeah, you can. Let's say we don't have bias right now, so this will
Okay.
be on the calculator. This looks like 72,674,400. These are the total number of parameters here. Okay.
Okay.
So this is your embedding layer. Now I'm erasing it. Just remember this number. 72 million was here. Clear all. Now we have LSTM layers. Two layers are there. Two layers.
Yeah.
What is your input? 400. What is your output? 250.
256.
Right. There are two layers. So each layer will have. We are doing this for LSTM or we are doing this for.
In this case,
We are doing
it's
this for
LSTM,
LSTM
but
only, no? Yeah, yeah,
you told for
yeah.
RNN.
No, no. We are doing LSTM only. Sorry.
Okay.
So each layer has 4 gates, right?
Yeah.
And so this will be your weight of input and weight of hidden. Okay. And there will be W of bias also.
Yeah.
Weights of bias also, right? So this is your hidden size into your input size. Fine.
Yeah, fine.
HH is hidden size into hidden size. Okay.
Yeah.
And your bias is there are 4 gates. Since you have 4 gates, so 4 into hidden size. This much is fine.
Yeah, it's fine.
Now we erase this everything. Clear all. Why it is happening like this? Okay. Moving ahead. Again pen. Okay. So your layer one has 4 into 400 into 256, right? This is your WIH, right? 409600. This is your WIH. Then you have WHH. That is 4 into 256 into 256.
Yeah.
Let's calculate it. This is 262144. 262144. Then your W of bias was 4 into 250. This is 4222102. Okay.
Yeah.
If you add
This is
all
for
of them,
one layer.
this will be 672,672,768. This is what calculator is showing. Fine.
Yeah, fine. We have to multiply it by 2, right? Or 2 layers.
No, you can't. You can't. 1 minute. Please wait. In your layer 2, 56. So it changes, na? So
Achha,
now
okay.
your WIH will be 4 into 256 into 256. Your WHH will be 4 into 256, 256. Okay. And then your bias will be 4 into 256. Fine. If you add them up,
Okay.
that will be somewhere between 525 and 312. 525, 312. This is what it value. Okay. Now your total
Okay.
number of LSTM parameters are 672, 672, 768 plus 525312. 525312. You add this 0. This is 780. This is 8. This is 911. So approximately 1,198,080. Something like that came here. And earlier what? 72 million was already there, right? Then finally you have a linear layer, right? That is from 256 was the input and your output is 1, right?
Yeah.
So your weights will be 256 into 1, that is 256, plus 1,
Plus
that
1.
is the bias 257. Okay. So the total
Okay.
number of parameters will be somewhere to 72 million, 1 million, and some 257. So something 73 million will come
Okay. All right. Got it.
here. Okay. Yeah. That's it, guys, from my side. We can close the session now, I hope.
Yeah. Good night, sir.
Yes, sir. Thank you. Good night.
Thank you.
Thank you, everyone.